we need to find a rectangular equation that's equivalent to the given pair of parametric equations. So we have a parametric equation here where one piece of the parametric equation describes how to create the x values of a function, and then the other piece of the parametric equation describes how to find the y values of a function. Of course, these are both of these different pieces, the yellow piece and the blue piece, are in relationship to a third parameter, t, or time. For this one, this is actually a particular type of question where the x value is related to a cosine function, and the y value is also related to a sine function. And in fact, if I just graph this in Desmos, this is the answer that we get. It's just a circle. Of course, don't forget, we need to graph these two functions, these two pieces, the yellow piece for x and the blue piece for y. We have to graph them within a certain time frame from 0 to 2 pi. Think of that as like the domain. That's like the domain for time, not necessarily the domain for x like we're used to. And so in Desmos, I graph it from 0 to 2 pi. And yet again, it gives us that circle. So actually, what we should notice is with these two trig versions of x and y, there's actually a special relationship that can relate the x and the y together. And that is with this Pythagorean identity, the good old classic Pythagorean identity of sine square plus cosine square equals 1. So, because really our ultimate goal is to squish these two things together to get some sort of equation like y equals something something with x's, some kind of function like that, good old x and y. And we're going to do that using, again, that equation, that Pythagorean identity. What I'm going to do is I'm going to make this equation equal to cosine. I'm going to divide both sides by 2. And so then I get x over 2 equals cosine of t. And then I'm going to divide this one also by 2. And then I get y over 2 is equal to sine of t. And then, of course, using the Pythagorean identity, that sine square of, I'll say t for time instead of theta, our time is our angle, and then plus cosine square of t, that just has to equal 1. So using that, I can actually put this expression, the x over 2, I will replace that in for cosine, and then I will replace the y over 2 for the value of sine. I'll go over here to point to the sine. I'm not plugging it into this function, I'm plugging in place of sine. So now it becomes not sine square, but it's actually going to be this y over 2, and then square. Plus, and again, instead of cosine square, it's actually going to be x over 2 square. I'm replacing cosine with x over 2. And that just has to equal 1. Oops, forgot to square that. Bam, there we go. So there we go. We've actually almost got our equation looking how we expect. I mean, technically this is an equation. I've now put it into an x and y function, rectangular equation, but we know it looks like a circle. I could even make this look more like a circle. If I square this is really just a y over 2 times y over 2. That's really just y squared over 4. And then this piece is really just an x over 2 times an x over 2. When in doubt, write them out. But that's really just an x squared over 4. And that just equals 1. And this actually kind of looks like the hyperbolic, or not hyperbolic, excuse me, the ellipse style of function. But we can make it even look more like a circle style if I just do one last little thing. I'm going to multiply everything by 4. So times by 4, times by 4, and times by 4. That makes it look like the good old circle structure. In fact, instead of a y square, I could rearrange this order and put it as x squared plus then the y squared equals 4. And this is like the good old circle equation with x squared plus y squared equals the radius square. And then, in fact, I kind of noticed that relationship that the radius must be 2, because 2 squared is 4. And then I have my equation, my circle there with the radius of 2. So that one is done. We wrote that pair of parametric equations, and we turned it into our answer down here. And it's just the good old circle equation for a rectangular function. Although circles technically aren't functions, right? But it is still like that kind of function notation, that good old rectangular style. Okay, let's do another problem. It says find a rectangular equation equivalent to the given pair of parametric equations. Again, we have two different equations. We have an expression or equation for calculating the x values of our function or our problem. And then we have an equation for the y value, and they're each independent, and they each are with respect to time. And of course, time, again, is sort of its domain of time. What period of time is from 0 to 2 pi. And if I graph this in Desmos, look at what we get here. It looks like it's a piece of a parabola. Notice it has a kind of a clear starting point and a clear ending point, where normally a parabola like keeps going forever. And that has to do with this period of time. We're only graphing within this time interval. So when we get our equation, we actually need to make sure we describe that it only is graphing from certain x values. In fact, we can go back to our first problem in a second and describe sort of just the domain it exists within this time interval. This problem, it makes more sense because we see it's definitely only a piece of what we would normally see, whereas the circle up above, we kind of saw the full circle, so we weren't really worried about it. But we'll return to that one in just a second. So here we go. Now this problem is different. This problem doesn't have trig values, so we're not going to use a trig identity to put the x's and y's together. What we're going to do is we're actually going to, in fact, this piece of it almost looks like what our equation is normally like a y equals and then a bunch of stuff, but it needs to have x's in it, like a function in terms of x. In fact, if I just think about a good old parabola, here's kind of the structure of a good old parabola in graphing vertex form, right? With our amplitude, our horizontal shift, and our vertical shift. But we do have an expression for x. What we're going to do is, we need to replace the t in there so that way it looks like good old parabola stuff, like good old x square stuff. So we just got to get rid of that t that's in there. We don't want to say y equals t square. So we're going to substitute or replace t. So over here we have a math problem that will help us replace t. For this one, I'm actually going to subtract 2 from both sides to get t by itself. So t is going to equal x minus 2. Now I can use this math and I can take this x minus 2 and replace t right here. T equals the x minus 2. So my equation is now going to say y equals, from this blue equation, y equals t squared, but I'm not going to put a t there. I'm going to put the equivalent stuff from this expression, that t can be replaced by x minus 2. And then actually, it's kind of what I see over here. When I look at this with my good old parabola knowledge, this is just a parabola shifted to the right 2. But here's the difference. The parabola to the right 2 would normally go forever that side and forever that side. But it looks like because our time is limited here, because our time is restricted from 0 to 2 pi, that means it's not going to graph the full thing because time is creating the x's and the y's for this parabola. We only want limited x's and y's because we have a limited time. So how do we figure that out? Well, first we notice it seems to start here at 2 and end somewhere just past 8. Well, what's the deal with that? Why is the domain limited from here to here? And how can we know for sure exactly what those numbers are? Well, remember, x is created by time with this yellow expression. So what we're going to do is we're going to consider, well, how much time do we get, or how much x do we get based on our time? Okay, so what's the smallest? Well, time is going to start at 0, but of course this isn't 0 for x. If x equals 2 plus time, well, if that time is actually 0, let me just put a big old 0 there. Where does the x start when time starts? And again, this is an equal sign. So time is 0 in the beginning, so that means x is 2 in the beginning. And now we see that, yes, this is a for sure 2 beginning. Let me actually clean some of this up here. This is actually now 2 for beginning our x. And that was kind of obvious and easy to see, but what's not so obvious is where does this thing end at? Okay, let's figure that out. Well, time is going to end at 2 pi. So when time goes to its fullest, we can actually see from our math expression that x equals 2 plus time. Well, when time is its fullest, that would make x be its fullest, its largest. So it would actually be 2 plus 2 pi. And then, if you get a calculator and you go 2 plus 2 pi, well, what is 2 pi? It's like 6 and a little bit, right? That would be 6.28, because it's 3.14, and if we double that, it'd be approximately 2 plus 6.28. So we know our largest time has got to be 8 plus 2, or excuse me, 8.28. If we just add the 2 plus the 6.28. So there we go. In fact, we could even just say it's 2 plus 2 pi if we want to keep it exact, but I'll just say it's about 8.28. So we know our domain for this, for our function here, has got to be from 0. Oh, no. 0 is time. We said it's from 2 to 8.28. So it's from 2 for x all the way to 8.28-ish, right? 2 plus 2 pi is officially what that's going to be. So as time goes from 0 to 2 pi, the x value is going to go from 2 to 8.28. And technically, we can even figure out the y value, like the range of this thing, like what would be the lowest and what would be the highest. Lowest seems pretty obvious. It looks like it goes down to 0. And that's because when time equals, in fact, let me write that a little lower, just like I did for the x's down here. When time is equal to 0, we can see that y equals time square. So if I square 0, I still get 0. So that would be my beginning. And then how high up does it get? Well, that would be when time, it appears that as time gets to be its fullest, its largest, so would the y value. So when time is actually equal to 2 pi, the y value would just equal 2 pi square. And if you take 2 pi and you square it, in fact, just to kind of estimate, 2 pi is what we said, about 6.28-ish. And if you square that, well, it's going to be, almost 40. In fact, 6 squared is 36. So 6.28 squared would be a little larger than that. I didn't crunch it on a calculator, but I would assume it's like 38 point something or 39 point something. So, and we can see that's right about it. In fact, I'm just going to say it's actually 4 pi square. I squared the 2 and I squared the pi. Now this isn't 4 pi squared like in parentheses. This isn't that. That's not what we're doing. I squared the 2 and I squared the pi, and so we get 4 pi square. That would actually be my range. My range would actually be from 0 all the way up to 4 pi square. Normally we just really describe the domain, because the domain will give us the range. The dependent variable will be created from the independent variable of x. So there's my answer here. I'm actually going to scroll back up to this problem that we had, because we really didn't talk about the domain or the range here, when actually maybe we should, now that we realize that as time changes, since time is restricted here, so is our x's. And we can really just see it from this graph. We can just say, hey, okay, our x is limited to what? What's our domain here? It looks like it's from -2 out to +2. And I know that's true because x is created from 2 times cosine. And what's the biggest cosine can get? Cosine can get up to 1 and down to -1. So the biggest x value can get is up to +2, because we have to multiply by 2. It's like 2 times 1, we get up to 2. But it could also go down to 2 times -1. Remember, that's the largest and smallest that cosine can get, is the 1 and -1. So that means when we double it, the biggest and smallest x could get would be -2 and +2. In fact, same thing for y. Sine can get up to 1 and down to -1. So when we double that each time, the biggest it could get is up to +2, and the smallest is to -2. So there we go. Now we've got both of these problems solved. We've got the actual math equation as well as its sort of restricted domain, its limited domain based on its limited time in existence. Let me get back down to the second one as well. And there we go.